Hello students, in this video we'll discuss several important properties of continuous functions. So let's suppose that f is continuous at x equals a, okay? That means, of course, that f needs to map a set E, which is domain, into R, and it must be the case that a is in this set E. Our first proposition is that the function f is bounded in some neighborhood of x equals a. Okay, and so here's what we can do. So we can so let's prove this. Here's the proof. Let's let epsilon equal 1, right? And so let's actually make sure that epsilon is 1, but it's sufficiently small so that we have a neighborhood. Then there is a delta greater than 0, such that if x minus a is less than delta, this implies that f of x minus f of a is less than 1. So in other words, in this neighborhood over here, what can we say? We know that if we're in the neighborhood from, so in the set from a minus delta to a plus delta, some neighborhood of this point A, we have that f of x is less than or equal to 1 plus the absolute value of f of a. So if we're really close to the point, if x is really, really close to the point A, we have this bound on f of x for this particular value of epsilon. So that shows that we are bounded in some neighborhood of x equals a. Okay, so we're bounded in a local neighborhood of x equals a. Now we can use some alternate criterion, alternate ways of characterizing continuity. So here's a proposition. That doesn't work so well. Let's do this one instead. Proposition. So f is continuous at a, so f continuous at a is equivalent to this for any sequence an, n goes from 1 to infinity, and the sequence needs to be contained in where? It needs to be contained in the set E where f is defined. For any sequence an contained in E converging to A, we have that the sequence f of n goes from 1 to infinity, converges to f of a. Okay? And this number 1 over here actually just directly follows from our sequential characterization of limits existing. So this is a consequence of the sequential characterization of limits. So this follows from sequential characterization of limits. It's an immediate consequence of that. Okay. The second one is just a topological version of this. That's 2. Okay. And that says that if V is an open neighborhood of the point f of a, then the preimage f inverse, the set of points that come from that open set, is an open neighborhood of the point A. Okay, and again, this is just a way of saying that if f of x, this is exactly just equivalent to what are the open neighborhoods of f of x. These things look like what? These look like f of x minus f of a less than epsilon over here, or y less than f of x, or basically these are y minus f of a less than epsilon. And these things over here, they're coming from what? Some other set, the preimage of those things which come from the points of x minus a less than delta. So in other words, this topological criterion is exactly equivalent to what? To the functional delta epsilon, the delta epsilon version of continuity, because we're using the metric topology on the real line. So openness is defined in terms of the metric topology. Thank you very much.